Okay, rigid body kinematics. This is our second class where we're talking rigid body kinematics. Last class, as I hopefully it was a review in today's bell ringer, we talked about some special cases of rigid body kinematics, and we talked about what we call absolute motion. Question?
Are you recording?
Just did, yes, thank you, I appreciate it. Okay, so we mostly talked about fixed axis rotation, roll without slip, pure translation. Today we're going to look at the more general form of general planar motion, which means that the body could potentially be doing both translation and rotation. But we're thinking more about how do we relate the motion of one particle on that rigid body to another particle on that rigid body. Okay? What turns out to be a really kind of beautiful analysis of the way this motion works is that you can take a general motion. Maybe you're taking this yellow bar that contains point A and point B, and you're doing some general planar motion through time, and maybe at some time step later, it ends up out here in space. So maybe this is time 1, and maybe over here is time 2. We can actually decompose this motion into a pure translation and then a fixed axis rotation. It's actually really neat if you look at it. So we're going to do this visually. I'm going to show you how this works visually. And it's actually going to come through in our equations for like velocity and acceleration. There's actually going to be a term that correlates to the pure translation part, and then a term that correlates with the fixed axis rotation part. It's really cool. If you're a nerd like me, I guess. Okay, so we have this very general planar motion. First, I'm going to show you how the translation portion of this works. So we might, for instance, take this body AB. I'm going to show you its initial position down here, and then just so you know I'm not lying, I'm copying and pasting this, so I'm not rotating it whatsoever. But I'm going to translate this body until point A gets to its final position. Okay, so point A's final position is somewhere up and to the right here, okay? So this is the translation that we'll do to it. So this is still point B. Now, we're not quite where we want to be at the end point, right? So just for reference, we'll see where we eventually need to get to. So that pure translation did not get us to our final position and orientation. We're not quite there yet. But point A is where it needs to be. Then I think it's actually kind of clear the way that I've drawn them on top of each other here is if I now do a fixed axis rotation of this body about point A, I just go, I can get B where it needs to go. That gets us to our final position. Okay, so let's draw that on our fixed axis rotation picture. Copy. We got our initial position. We got our intermediate position. And we got our final position. Whoops. Okay, so we took the previous position and we rotated it about point A by some angular displacement d theta. So this is initial. This is final. Okay, so visually we can see that this is the case. We can see that we can translate and then rotate. When we look at our velocity equations, we also, I was going to do this in 3 steps, my bad. In our velocity equation, it also comes out beautifully. And so I want to remind you really quick of what the fixed axis rotation equation was for velocity. So we said that if we have a body that is rotating about a fixed axis, and we want to know the velocity of some point P on that body, then we simply need to take omega cross r. Okay, so the vector for the angular velocity crossed with r, where omega here is angular velocity of the body. And r, who remembers how we explain r? Yes?
Just asking, are you recording?
I am, yes, thank you. Who remembers how I describe r? The vector that goes from where to where?
Anywhere on the axis to the point.
Anywhere on the axis of rotation to the point I'm concerned about. Very good, Annabelle. Any vector from the axis of rotation to the point P. So here's the beauty of our general planar motion, is that if I want to understand the velocity of point B, and I know something about the velocity of point A, I can write velocity of B like this. Now, which of these terms do you think correlates with the translation, and which one correlates with the fixed axis rotation?
Angular velocity is translation.
This one?
Oh, I'm sorry.
This one?
Regular velocity is translation. Angular is rotation.
Very, very good. Okay, you'll notice this term, it's that one, omega cross r. This is the part that takes care of the fixed axis rotation part of that motion. V is your translational velocity. Okay, so here we have a pure translation. And then the rest of the body needs to do a fixed axis rotation about A. It's Catherine Jolie, right? Got it. Okay. Just like we did for fixed axis rotation, let's also go through every single variable and define what this is. Okay, so VB is the absolute translational velocity of B. Okay, so what do I mean by absolute? Samuel?
Some of its components, or like the sum of both.
Not necessarily. When I say absolute, yep.
It's only in reference to itself.
Kind of. It's in reference to a very particular coordinate system. Is it a coordinate system that's moving about in space, or is it a coordinate system that's Earth fixed? It's a fixed coordinate system, right? For instance, this Cartesian coordinate system right here. So absolute means that from a standpoint where you yourself are not moving in any way, this is what the velocity of point B looks like it's doing in space. Okay? This is different than if you were to be observing from sitting on the rigid body itself. Where you're zooming around on the rigid body, the velocity of B is going to look very different to you. And in fact, it should not be moving relative to you. right? If you're also on the rigid body. Okay, so it's absolute, meaning it's relative to an Earth fixed coordinate frame. And then what do I mean by translational? I just mean that this is not your angular velocity. This means this is the rate of change of your position. Okay? All right, VA, very similar. The absolute translational velocity of point A. Omega has the same definition as previous, so angular velocity of the body. I just want to re-emphasize this because this throws some people for a loop. Angular velocity and angular acceleration are properties of a rigid body, not of a point. Yes, ma'am? Yep. That okay? Okay. And then lastly, you tell me, how do I interpret this symbol here? What B with respect to A? When we talk about Cartesian coordinate system, this R vector is what? Position, velocity, or acceleration? Position. Okay, so we say this is the position vector from A to B, or of B with respect to A. Okay, let's do a very similar song and dance with acceleration. I'm going to remind you of what the fixed axis rotation for acceleration looks like, and then show you how that shows up in the general planar motion equation. So, from our last class, if a body is doing fixed axis rotation, and we want to know the absolute acceleration of some point on that rigid body, the acceleration of this point is alpha cross RP plus omega cross RP, where alpha here is the angular acceleration. Of the body. Okay, general planar motion, acceleration. I'm running out of room here, so I'm going to do it way down here. If I want to know about the acceleration of some point B, and I know about the acceleration of some point A, I'm in luck. Uh-oh. Okay, so this term here is the translation portion. And this whole nastiness looks exactly the same as our fixed axis rotation equation, so this is due to the rotation. Acceleration A here is absolute translational acceleration of point A. AB, oops, there we go. All right, we've already covered what is alpha, we've already covered what is omega, and we've already covered what is RB/A. Those have the same definitions as the prior equation. Okay, one really important thing to note. These two equations are the crux of what I need to cover today, okay? So we're going to do one single example. It's a pretty long example though, okay? So we'll walk through it slowly. We're going to do one example, but one thing to note is when you're looking at your equation sheets, a lot of these equations can start to look very similar to each other, right? So this general planar acceleration has almost all of the same components as the fixed axis rotation equation. So a really, really important thing to know is when is it appropriate to apply these equations and when is it not. You have to be very, very careful. So if you apply only this equation when you're not doing fixed axis rotation, things are going to go wrong. But also note that when we're talking about A and B here, in both the velocity and the acceleration, we are specifically referring to 2 points that are on the same rigid body. On the same rigid body. That's important because some funny things happen later on when we go back and review prior material, and I say, I have 2 points, A and B, that are moving around in space with no relation to one another. I want you to find RB/A, or acceleration of B/A. If these 2 points are not on the same rigid body, you cannot use today's equations. It doesn't work. Okay? So, big part of this class is understanding when it is appropriate to apply these equations and when it is not. Okay. I think most people are done writing. So let's hop to this example. Let me make it bigger. All right, this question is asking us to determine the angular acceleration of link AB if link CD has the angular velocity and angular deceleration shown. Let's read that again, and I'll try to highlight as I go. Determine the angular acceleration of link AB. That's this one. If link CD, that's this one. Oh, that was a terrible highlighting color. Yeah, that's better. Has the angular velocity and angular deceleration shown. So these apply only to body CD. Oof. So I just spent like 5 minutes reiterating that these equations are only for 2 points on the same rigid body. And then Dr. Higgins goes wild on you and says, now consider 3 different rigid bodies. Have fun. Kind of mean. Okay? But these rigid bodies are not just flying about all willy-nilly. They have these really important connections called pin joints. These pin joints mean that there is a common point that is shared on 2 rigid bodies. Okay? So the translational velocity of point B can be described as though it is attached to body AB, or it can be described as though it is attached to body BC. And you can actually set those 2 equations equal to each other, right? Regardless of whether you're viewing the motion of B as it relates to AB, or whether you're viewing the motion of B as it relates to BC, it should have the same velocity and acceleration translationally. Otherwise, it means they're not actually pinned, right? That would mean that it would be coming apart. So we're going to have to rely on this. And in fact, one of the ways that I like to start these problems is thinking about working from an area of known information towards the area of information that I want. Okay? So I have a lot of information about what's happening on the right side of this linkage, but I want to know what's happening to the left. So one of the first things that I will try to do, probably, is to describe the velocity of point C given what I know about how CD is moving. Okay? Let's also notice some other things. Am I able to write down anything special about the velocity of, let's say, maybe point D? If I wanted to write down the velocity of D, what would that be? Samuel says 0. It certainly can't move left and right because it's pinned right where it's at, and it certainly can't move up and down because it's pinned right where it's at. Very good. So we can say point D has a velocity 0I plus 0J. That might be useful. Similarly, it also has 0 acceleration. Is there another point very similar to that? Point A, yes, absolutely. We might need to use that information too. Okay, so things to notice. So that's kind of the sneaky thing about dynamics problems, is sometimes the information that you need in order to solve the problem is hidden in the picture of the system and is not actually described in words in the problem statement at all. Okay, so these are things that you need to notice. And I try to do that a lot on my homework solutions, is I'll write needed to notice this, and I'll write out the equation that you needed to notice. Okay? Okay, whoops. Let's see. Now, can I write what's given? Can I write this in any better way than this? So they've given these values to me as scalars. But in all of these equations that I just gave you, you have to write them as vectors in order to do cross products and whatnot. Can we try to make it look like a vector? How would we write it? Let's say I want to write omega CD as a vector. How would I do that? Well, have I set a coordinate system yet? Oh, that's probably important. What should we use? Maybe a Cartesian coordinate system? I have no reason to think not. So I'm going to do, we'll say X goes to the right, Y goes up, which means that Z comes out of the page by right-hand rule. Yes?
Would be the positive k-hat direction.
Positive k-hat direction. Let's look. It says omega goes that way. So if I use my right-hand rule and I follow the arrow, my thumb points out of the page, which is positive Z. Very good. So it's 2 k-hat. Great. Just the magnitude and then the axis of rotation direction.
Does deceleration not matter? It says deceleration. Wouldn't that usually make it?
It won't. Yeah, it doesn't matter as long as you follow whatever coordinate system convention you set and you stay consistent with it. So all that matters is that the direction of this one is opposite the direction of this one. So what happens when we try to write acceleration as a vector? The angular acceleration. It's going to be into the page, which is negative k-hat, 4. Yep. So words like deceleration can sometimes be confusing. It doesn't always mean it's negative. You have to set a coordinate system before you can be sure it's negative. Okay, I'm going to give you a quick hint. My hint is that I want to work from point D to point A, and the first thing that I will do is relate basically the velocity of point D to the velocity of point C. Hint is work from point D to point A. And the first thing I'll do is relate velocity of D to the velocity of C. Actually, I'm going to write that a little bit more broadly. We're going to do both velocity and acceleration, so I'll just say relate D to C. That better? Okay. All right, so do we have everything that we need to know? Let's see. I certainly have an expression for the velocity of D. We did a great job of interpreting what was given as an angular velocity vector. And now I need to find the position vector that goes to C from D. So sometimes it can be helpful just to draw that. So going to C from D. So this guy here is R, right? 0.9 j hat, right? Just add these two lengths and it's purely in the j hat direction. All right, so I'm going to start plugging in. So I have 0 I hat plus 0 j hat. That whole thing goes to 0. That goes away, and I'm left with fixed axis rotation. Okay? Omega was 2k hat cross 0.9 j hat. Okay, just do a simple cross product. 0, 0, 2, 0.90 should have some amount I minus some amount j plus some amount k. 0 minus 0.9 times 2. J hat, I'll have a 0 minus a 0. K hat, I still have a 0 minus a 0. Okay, so VC should be equal to minus 1.8 I hat. And we can even visually look to see if we agree with that. So if this long arm is rotating this direction, C is right at the top of that circular motion, so it should only be moving directly to the left. Yeah? That looks right to me. It seems reasonable. Okay? Very good. Let's do acceleration. Acceleration of D. What is it?
0.
0. Someone's awake. Great. Goes to 0. So AC equals alpha, which is minus 4k hat, cross RCD, which we said was 0.9 j hat, plus, I'm going to be a little sneaky here. I'm going to take omega cross, what is omega cross R? We already found it. That should be this, right? Yeah? I'm just going to save myself a cross product. I don't need to recalculate what omega cross R is. Is anyone uncomfortable with that? Okay. All right, so we still have two cross products to do. This first one, I, j, k, 0, 0, minus 4, 0.90, I minus j plus k. I always do it this way because I tend to forget the minus j part, and this keeps me honest. So do whatever tricks you have to do to keep yourself honest. All right, I, 0 minus negative 4 times 0.9. J is going to be 0 times 0 minus 0 times negative 4, so 0 minus 0. K is 0 minus 0. Okay, so that's just the first cross product. Now the second product is I, j, k, 0, 0, 2 minus 1.800. I minus j plus k. I is 0 minus 0. J is 0 minus 2 times negative 1.8. K is 0 minus 0. Okay, so A sub C, I should get, the two negatives cancel here, I'll get a positive 3.6 I hat. Very good. Okay, that's still not what the problem is asking us for. I still want to work my way over to body AB. Okay, so the next thing that I can do is do that same song and dance, but relate the velocity of C, which I now have an expression for, to the velocity of point B. Let's relate C to B, because these two things are also on the same rigid body. Just as a foreshadowing, once I do this, I'm going to have to do this song and dance one more time. The last thing I'll do is I'll relate A to B, and I'll end up with two expressions for the velocity of B. One is as seen from this elbow, and one as seen from this body, and I will set those two equal to each other and solve for my unknowns. Okay? So, that said, I want you all to take a few minutes to attempt at least the next step. So, attempt doing exactly what I just did, but now relate C to B. One thing that's a little wonky, just to keep your eyes out, is you're not going to immediately know an expression for omega AB. Yeah. Wait, sorry. Omega CB. You will have to leave CB as an unknown. Okay, we don't know how that body is rotating. We just know how point C is translating. Okay? Okay, I'm going to leave this here in case it helps you with the other part. Oops. All right, let me give you one more hint. One more hint about this omega CB thing. So we don't know the amplitude of omega CB, but we do actually know the axis of rotation. Why would I say I know the axis of rotation? I know that on a two-dimensional plane, two-dimensional problem, I can either be rotating to the left, like this. That would point my thumb out in the positive k-hat direction. Or I'm pointed this way to the right, which would be a negative k-hat direction. Okay? So what I can do is I can say, all right, well, I don't know amplitude CB. I don't know whether it's positive or negative, but I do know that it points in the k-hat direction. So I'm allowed to do this. And what'll happen is if we assumed the positive k-hat direction, but when we solve, we're going to have to solve a system of equations later. If we get a negative value for omega CB, it just means that we chose the direction wrong. Okay? So the positive or negative will come out in the wash when we solve our system of equations. But writing it this way means that we can plug it into a cross product more nicely. Right?
Can you do the same thing for alpha, or are we?
Absolutely.
We don't like relate it to.
Nope. Alpha is also it can only be in the k-hat direction. Simply because this is a two-dimensional problem. If it were a three-dimensional problem, we're kind of screwed. It could be any which way, right? But because this is 2D, we have this simplification. Make sense?
Yeah, I thought it'd be.
Everything about this is in the plane. So this thing can only rotate that way and that way. It can't go into the page. Nothing can go into the page or out of the page. So if anything rotates this way, it's directly out of the page. If anything rotates that way, it's directly into the page. Is that better? Yeah.
So we have,
Those are the same
are we
thing.
assuming?
Those are the same thing. This vector is the same as the addition of these two vectors, right?
Yeah,
Some amount in the I hat, some amount in the j hat.
yeah.
Okay, I'm seeing some blank faces, so I'm gonna start taking over. Okay. I want to find velocity of B. Velocity of C is what I found in the last part of the problem. So I can go ahead and plug in here, minus 1.8i. Omega CB is what we don't know, but I just covered why we're allowed to write omega CB in the k-hat direction, crossed with RB/C. So this is the vector that points to B from C. So the vector that points to B from C is this one. So it looks like I'm going in the negative I hat direction by 0.6, and then the negative j hat direction by 0.6. So we should have minus 0.6i minus 0.6 j hat. Okay, that's as good as I can do there, aside from just evaluating the cross product, which I can go ahead and do. So we'll do I, j, k. I have 0, 0, omega cb, and then minus 0.6 minus 0.6, 0. This will be I minus j plus k. Okay, I hat 0 minus negative 0.6 times omega cb. J hat 0 minus negative 0.6 omega cb. And then k hat 0 minus 0. Okay, so my expression for VB, I don't want to forget that little I hat component here. So let's do 0.6 omega CB minus 1.8, all in the I hat direction. Good. And then I end up with 3 negatives on the j hat. So minus, minus, and minus. So I get minus 0.6 omega CB in the j hat direction. Okay, now that is as good as I can get for this step in the problem. Okay, so I'm going to box it because it's going to be important. And then we're going to move on to acceleration. All right, so acceleration of B relates to acceleration of A, which we have from before. 3.6i minus 3.6j plus alpha, I need to write carefully. So this will be alpha CB in the k hat direction crossed with RB slash C, which we already found. So that was minus 0.6i minus 0.6j plus omega CB was omega CB k hat cross with omega cross R, which should just be the result of this cross product that we already took for velocity. Question? For the J, there are 3 negatives. I have the minus, and the minus. Yep. So that's why I write this out ahead of time, because I always forget it if I don't write it out ahead of time. You're welcome. Okay, let's do 0.6 omega CB I hat minus 0.6 omega CB J hat. All right, I got 2 cross products to do. I, J, K, 0, 0, alpha CB, minus 0.6, minus 0.6, 0. I minus J plus K. All right. 0 minus negative 0.6 alpha CB. J is 0 minus negative 0.6 alpha CB. K is 0 minus 0. All right, let's do the other cross product. 0, 0 omega CB, 0.6 omega CB, minus 0.6 omega CB, 0. 0 minus 0.6 omega CB squared J is 0 minus 0.6 omega CB squared. 0 minus 0. Okay. So acceleration of B equals 3.6 I minus 3.6 J. Yes, Samuel?
Did you remember the minus 1.8 in the I direction, maybe? And your W cross?
Over here? No, because it's omega cross R, not VC plus omega cross R. So I want to reuse math as much as I can, but not too much. Okay. Where was I? All right, we got the first cross product we need to add in. So I've got plus 0.6 alpha CB I hat. 3 negatives makes a minus 0.6 alpha CB J hat. It's the result of this first one. Plus 0.6 omega CB squared plus 0.6 omega CB squared, I J. Wait, something's not right. No, that's right. That's right. Okay. Let me group my I's and J's. 3.6 plus 0.6 alpha CB plus 0.6 C omega CB squared. All in the I hat. Minus 3.6 minus 0.6 alpha CB plus 0.6 omega CB squared J hat. Okay. Oof. Lots of algebra. Last song and dance is we need to relate what we know about point A to the velocity of B. We'll get another VB and another AB, and then we can set these equations equal to each other. All right, last bit. Relate A to B. Okay, so we'll have velocity of B equals the velocity of A plus omega AB cross R B slash A. What's velocity of A? 0. It's pinned to the ground. What's the acceleration of A? 0. It's pinned to the ground. Whew. We at least get some sort of simplification. All right. Omega AB goes about what axis of rotation? What's the axis of rotation for a 2D problem? K-hat. Some amount in the K-hat direction. I don't know how much. We're going to leave it as an unknown. Cross RB/A. That is the vector that points to B from A. Let's look at that. To B from A. I'm thinking 0.3 J hat. 0.3 J hat. All right, not too bad. Another cross product. Zero minus 0.3 omega AB, I hat, minus 0 minus 0, J hat, plus 0 minus 0 K hat. VB equals minus 0.3 omega AB, I hat. Question?
Wait, so when did you get the angular velocity K hat for
Yep. So for a two-dimensional problem, when I say 2 dimensions, I mean that this entire mechanism lies in the plane. It doesn't make sense for this thing to rotate out this way or into the board. Do you agree? So the only way that bodies can rotate in the plane is to rotate this way or to rotate that way. If they rotate this way, I do my right hand rule, my axis of rotation is perfectly out of the board. If I rotate the other way, my hand rotates the other way, axis of rotation is perfectly into the board. Those are both along the K hat direction. The negative just gets lumped in with that unknown amount, omega, whatever. Okay. So for a two-dimensional problem, only for a two-dimensional problem, the axis of rotation is going to be in the K hat direction. Okay. Great question. Okay, let's do acceleration. AB equals alpha AB K hat cross 0.3 J hat plus omega AB K hat cross this thing minus 0.3 omega AB I hat. Okay, we'll have 2 more cross products and I'll end up with an expression for acceleration of B. I only have 1 minute, so I don't think I actually have time to finish this up. But the plan going forward that I'll finish in a separate video is I'm going to set this acceleration of B that I just found equal to this acceleration of B. I'm going to set my I hat components equal to each other. That's one equation. I'll set my J hat components equal to each other. That's another equation. And then I'll do the same thing for velocity of B. I'll take this velocity of B, set it equal to this velocity of B, set the I hats equal, set the J hats equal. That gives me 4 equations. Think back to your system of equations. How many unknowns can I solve for if I have 4 distinct equations? 4 unknowns. What are my 4 unknowns in this problem? Well, in this equation, it looks like I have omega CB. It's 1 minute left. Give me 1 minute. Omega CB. In this equation, it looks like I have an alpha CB. That's another unknown. In this equation, I have an omega AB. In this equation, I'm going to have an alpha AB. Those are the 4 unknowns. I'll have 4 equations. Solve the system of equations doing algebra. We can solve for all 4 of those unknowns. And those unknowns are what the questioner is asking us for. Okay? Reason I like this problem is you have to do this rote thing of relating 2 points on the same body over and over and over and over again. So it's really like 4 problems in one. Thank you. I'll see you guys Thursday. Okay, so I ran out of time to finish this example in class. This is the relative motion example with this frame made up of 3 rigid bodies. I'm going to start off right where we left off in class, which is we were relating the kinematics at point A to the kinematics at point B. And we did that for velocity, and then we're going to do the same thing for acceleration. So we went ahead and filled out our relative acceleration, or not relative acceleration, but our acceleration equation that relates A and B, but I did not get a chance to do the cross products. So let's do that now. I'm going to give a little space. So this will be the first cross product, and then this will be the second cross product. So I'm going to do I, J, K, 0, 0, alpha, A, B, 0.30. And then later I'm going to have to do I, J, K, 0, 0, omega AB, 0 minus 0.3 omega AB, 0. Oh, wait, that's I hat. Oops. Not J hat. Omega AB, 0, 0. Okay, let's do these cross products and find acceleration of B. Okay, so I'll have I hat minus J hat plus K hat. Right, forward is 0 minus 0.3 alpha AB. This one and this one will give me 0 minus 0 and 0 minus 0 again. Okay, so that's pretty simple. So minus 0.3 alpha A B I hat. And then over here, 0 minus 0. J will be 0 minus negative 0.3 omega A B squared. And then 0 minus 0. Okay, so I see 3 negatives here. So 1, 2, 3. So I'll have a minus 0.3 omega A B squared J hat. Okay, so it looks to me like AB up here equals minus 0.3 alpha AB I hat minus 0.3 omega AB squared J hat. Yep, and that's what I have in my notes. Okay, so now I have 2 sets of expressions for the velocity of point B and for the acceleration of point B. And I can set them equal to each other, okay? So I'm going to go back up and I'm going to set this VB equation equal to this VB equation. And then separately I'm going to set this acceleration of B equation equal to this acceleration of B equation. And then we'll see if we have enough to solve our problem. Okay, so I'm going to copy and paste all of this information to a new slide just to try to make it clean. And I'm grabbing too much extra stuff. We'll do copy. Paste. Copy. Paste. Give myself some room to do algebra there. Oops. Get another page. And we'll do alpha, not alpha, acceleration. And acceleration. There we go. Okay, let me clean this up just a little bit. And now, I'm going to set the I components equal to each other and then the J components equal to each other. So my I equation will be 0.6 omega CB minus 1.8 equals minus 0.3 omega AB. And then my J equation is just minus 0.6 omega CB equals 0. Okay, so we know omega CB must equal to 0. And if we plug that in here, in the I equation, we should see minus 1.8 equals minus 0.3 omega AB. Should be able to solve that omega AB equals 6. Okay, great. That's 2 unknowns figured out. Now let's look at the other set. Let's look at acceleration of B. Again, I'm going to set I components equal and then J components equal. So I equation minus 0.3 alpha AB equals 3.6 plus 0.6 alpha CB plus 0.6 omega CB squared. And I'm going to fill in what I know too. So I know omega CB is 0 from above. So that goes to 0. All right, but I'm left with 2 unknowns. I'll have alpha AB and alpha CB. So I can't solve this quite yet. I need to set up my J equation. So I should have minus 0.3 omega AB squared equals minus 3.6 minus 0.6 alpha CB plus 0.6 omega CB squared. Again, this goes to 0. And now I have, I can also plug in omega AB, which is 6. So I get minus 0.36 squared. And now this equation is only in terms of alpha CB, so we should be able to solve that alpha CB equals minus 36. And now I can plug this in my I equation. So I'll have minus 0.3, that's AB. I want to solve for AB. 0.3 alpha AB equals 3.6 plus minus 36. Okay, so alpha AB then, sorry, this is not correct. This comes out to 12. And then this becomes 12, and AB is minus 36. Okay, now let's go back and make sure we have what the problem is asking us for. So, determine the angular acceleration of link AB if link CD has the angular velocity and angular deceleration shown. So I want alpha AB is what I really wanted to know from this problem. So let's make that one abundantly clear. So alpha AB equals minus 36 radians per second squared. And that's the end of that problem.